Check that out. Can you see that? This is not the simplest circuit, but the best one to start with. So if you look here, you can see I actually have 3 light bulbs. I glued them on here for you. Okay, so here I have 2 1.5 volt batteries. So this side's positive, and then I have a wire. It comes out here to this light bulb, and then from that light bulb it goes to that light bulb, and then goes back. And then I have another wire that goes from here straight to there. Now can you see, they're all the same light bulbs. Can you see which one's brightest? So this one is brighter than those two. I don't know if you can tell. It's kind of, let me hold it like that. Yeah, it's brighter. Come on, that's brighter. Okay, so we are going to analyze this circuit, and I'm going to show you the 2 circuit rules. The loop rule and the junction rule. And that's what I'm going to show you, and then we're going to analyze the circuit. And so we're going to assume this is a 3 volt battery, because it's 2 1.5 volt batteries. And we're going to assume each one of these are the same resistance. I'm just going to pick 100 ohms, but that's not quite true, but that's fine. Okay, so I'm going to unplug this, turn it off. Okay, I'm going to put it down. I'm still here. I already drew the diagram up here. This is one thing that is kind of difficult. It's kind of, how do you go from an actual diagram like that to a picture like this? It does take practice, okay? So this is a circuit diagram. Instead of for the battery, we draw this short and long line, where the long line represents the positive side of the battery. So I'm just drawing it as one battery. And then the light bulbs I'm drawing as resistors, so you just see those squiggly lines. Okay, so that's my circuit. So I have 1 bulb connected to the battery, and then 2 bulbs connected. Now you may say, wait, but there weren't these points over here. But it doesn't matter. If I drew these wires going straight down to there, since if these wires have no resistance, it's equivalently the same, and this is easier to analyze. Okay, so it's just hard to get into practice with that, but this is actually what's going on. Okay, so let me go over the 2 rules. The loop rule. So, remember that the change in potential is essentially adding up electric fields over some path. And that's how we got it, okay? If the electric field's constant, it's easy, but if it's not easy. But nonetheless, we could do that. We can make an electric potential if the change in potential does not depend on the path. So it doesn't matter which path I take, I get the same change in potential. So now, let's assume that I start here and I end there. It doesn't matter what path I take, I have to be at 0. If I start and end in the same place, then it has to be a 0 change in potential. So that means that a loop, any loop, delta V is 0. So if I go around this loop and add up the changes in potential, 0. If I go around this loop, the big loop, changes in potential, guess what it is? 0. If I go around this loop and I didn't have a battery, 0. That's the loop rule. I'm going to show you how to use it. Junction rule. This says that I in equals I out. A junction is where 2 or more wires meet. So that's a junction. I have a wire there and I have a wire there. It's a boring junction, but it is indeed a junction. Okay. So the current coming into that junction has to be the current coming out. I mean, that kind of makes sense, right? If I have current coming in and I have more current coming out, where did it come from? If I have more current coming in than going out, where is it all stored, right? It's just, there's nothing there. So that one's a boring one. These are 2 more junctions. I have 3 wires. So the total current coming in has to be the current coming out. This really is just another way of saying charge has to be conserved. Okay, I can't just have that charge disappear and go nowhere. It's still conserved. So the total current, if you take all the currents and add them up going in, they have to be the current going out. Okay, so now those are my 2 rules. My loop rule, my junction rule. I'm going to use that to find the 3 currents in this circuit, assuming my battery is 3 volts and assuming that each of those R's is 100 ohms. Okay, so that's what we're going to do. I've already picked the currents, okay? Now, in some cases, you may not be able to do that. You may say, I don't know which way the current's going, but I can still label them. So in this case, I say this is the positive side of the battery. And so current's going to come out where we're using conventional current is the flow of positive charge, even though that's not usually what happens. That's okay. We'll still get an answer. So we have positive charge coming out this way, and then it comes up, and we'll call that I1. It comes to this junction. Some of it goes through the top resistors, and some goes through the bottom resistors. So the bottom one we're going to call I2, and that one we're going to call I3. We're going to solve for those three. Okay. Let's do it. Okay, so first I'm going to use the loop rule. I'm going to use this loop. I'm going to go around here, just like that. Actually, I'm going to go the other way. I'm going to go from here. I'm going to go from here all the way around. Okay, so let's add up the potentials as I go around the loop. So if I start here and I go to there, I crossed over the battery. So the change in potential, since I'm going from the minus side of the battery to the positive side of the battery, is going to be plus 3 volts. So I'm going to say that's just going to be, let's say delta V equals 0 equals EMF. That's the change in potential. I'm going to leave it as a variable for right now. Okay. Now I come up here. There's no changes in potential because it's just a wire. And now I'm coming over here. I'm going with the current, and I cross that resistor. If you're going with the current, then the voltage drop across the resistor is going to be minus I1R. So you get a voltage drop going in the same direction as the current. If I was going this way, it would be plus I1R. But I'm going with the current. And then I get back down there, so that's it, 0. Right away you can see I can solve for current I1, and I'm going to do that. Okay, so I get EMF minus I1R equals 0. EMF equals I1R. I added I1R to both sides. Now I'm going to divide both sides by R, and I get I1 equals EMF over R. That's important. I'm going to leave it right there. I'll put in the numbers shortly. Okay. Now, let's do, what do I want to do next? I want to do it in the right order so it makes the most sense. So I make it clear to you. Let's do next the junction rule. And there's only 2 junctions here, right? I have this one and this one. And it doesn't matter which one I'm going to pick. They're actually the same thing. So let's pick that one. The current coming in is going to be I1. The current coming out is I1 plus I2. I mean I2 plus I3. Okay, so that's my junction rule. Now you'll notice that if I plug in my values here, I already have a number. I can get a number for I1, but I don't know I2 and I don't know I3, so it doesn't really help me. If for some reason you didn't know the direction, if I picked I3 is coming this way, and you can do that. Okay, at the end of the experiment, when you solve for a current, you get a negative number, that just means you got the direction wrong, and just switch the direction. Okay, but you see here I have really 2 variables I don't know. I know I1, so and I only have 1 equation, so I need another equation. So the only way I can get another equation is to do another loop. So in this case, there's actually 3 loops in this problem. I have the one I did, I have this one up here, the smaller loop, and then I have the big loop. Okay, so I need one more loop. I'm going to pick this one up here. I'm going to go from here around that loop like that. So if I start going this way, I'm going against the current. So I have the voltage drop across this is going to be plus I3R, and this is going to be plus I3R. So I get I3R plus I3R. I'm a terrible sloppy person. And then I should do, then I'm coming over here. Now I'm going the same direction as I2, so I get a voltage drop of minus I2R. And then I get back to the beginning, so it's equal to 0. Okay. So I have I3R plus I3R is 2 I3R. Add I2R to both sides, I get equals I2R. Divide both sides by R, and I get 2I3 equals I2. Okay, so that's another important thing. Now I can take this and put it in here. Okay, so let's put, instead of I2, I'm going to write this as I1 equals 2I3 plus I3. So instead of I2, I wrote this equation, I2 is equal to 2I3. So it's just substitution. Okay, so now I get that is 3I3 equals I1. So now I can solve for I3. So I3 equals I1 over 3. And then I can use this equation to solve for I2. So let's solve this for I2. That's good right there. So now I2 is going to be I1 minus I3. Right? Because if I just subtract I3 from both sides. So I get I2 equals I1, which I'll leave as I1, minus I3, which is minus I1 over 3. So I2 is going to be 1 minus 1/3, so it's going to be 2/3 I1. I'm really done, but let's put in the numbers. Okay, so this is going to be equal to the voltage of 3 over 100 amps. I'll leave it like that. So 0.003 if you like. Okay, 0.003. Now, I3 is going to be equal to this 3 over 100 divided by 3. So this is going to be 1 over 100 amps. And this is going to be 2/3 of that. So this is going to be equal to 2 over 300 amps. I did it. I found the 3 currents. Yay us.